Hey, it's Gale Banks. This is Killing a Duramax Part 4, and I've built this. In the last episode, I showed you why the compressor and the turbine on this turbocharger are out to lunch. And there's going to be a lot more on that. But first, I want to show you about this. What we've done to duplicate the mistakes people commonly make with their air intakes. Also, we're going to show you what happens when you go to higher altitude. Guys are talking horsepower all over the place. But what really matters to me and what really matters to you is the power that you can make where you're at. What is this ugly ass thing, you might ask? Well, it's an intake air density control. I can regulate the air density going into the compressor of the turbocharger and duplicate various conditions from high altitude to a crappy, lousy air intake system, especially one with a filter element naked under the hood with a hot mother engine. What we've done is we've set up a device and a test that'll show exactly how much horsepower you lose if you screw up or if you live at high altitude. To help you understand what we're doing here, I'd like to take you back to high school. Let's go out in the shop. Okay, I want to get to some elemental stuff here. I want to take you back to the four-stroke process. Most all of you have been exposed to this somewhere in your education, or if you're an enthusiast, you've heard it. Most engines today, in trucks, cars, whatever, are four-stroke, and they're either spark ignition or compression ignition. That's the basis of it. What are those strokes? Crank revs 2 times, you go through the 4 strokes. Piston drops, intake stroke. Piston rises, compression stroke. Piston drops, power stroke. And the piston rises, exhaust stroke. Let me take you through the elements of all of those, but I want to make a comment right up front. Of those 4 strokes, only one makes power, the power stroke. The power stroke puts horsepower into the crankshaft. The other 3 strokes take horsepower out of the crankshaft to run their process. So you want to minimize that parasitic loss from the crankshaft. You want to maximize the power resident in the crankshaft. Now, where does that power go? It goes out the flywheel into the crankshaft, to the transmission, and ultimately to the road surface, and it pushes the vehicle. But there's another parasite, and people don't talk too much about this, but I'm going to talk about it because I'm doing an engine for a monster truck right now that has this parasite on it, and it's called a supercharger. Like the 3 parasitic piston strokes, it also pulls power out of the crankshaft. Well, where did that power come from? The power stroke. Here's why I like turbochargers, and blowers aren't really my weapon of choice. My tool for performance for 50-some years has been the turbocharger, because it makes better power at the same cylinder pressure. Well, what's this cylinder pressure thing about? On the power stroke, pressure is built. The combustion forces the piston down. My message is you only get so much cylinder pressure and something fails. You either fail head gaskets or some other physical part. If you're running a turbocharged engine, you don't use energy off the power stroke to run the turbocharger. You get all of it. There's no parasite on the front of the crank driving a belt, chain, gears, whatever, to drive a supercharger. Whatever you can make to that cylinder pressure limit goes straight to the crankshaft. You don't remove part of what you've made within that limit to drive this parasitic thing on the nose of the crank, this supercharger. You get it all. Well, where do you get the energy to drive the turbocharger? You get it on the exhaust stroke. You're still parasitic, but you're getting everything you can out of max cylinder pressure. You're getting everything you can out of the power stroke. It's far less of a problem in terms of parasitics if you take it off the exhaust stroke. You're within the structural limit of the engine, but you're utilizing all of that to drive the crankshaft. So let's talk about the intake stroke. I want to give you something here, and that is all induction is forced. What do I mean by that? When the intake stroke occurs, the piston is moving so fast, it's pulling an almost perfect vacuum above the crown of the piston. How fast, you might say? Well, I did some math, and it's pretty remarkable. At 3,000 RPM, you're running 50 revs of the crank per second, and the intake stroke takes 1/100th of a second. At 6,000 RPM, that's 100 revs per second, the intake stroke takes 5/1000ths of a second. And just for grins, years ago, Cosworth did a V8 Formula One engine that turned 20,000 RPM, and the intake stroke took 1.5 thousandths of a second. An astoundingly quick movement of the piston. In a naturally aspirated engine, the ambient air pressure forces the ambient air density into that lower pressure. There's forced induction. It's called naturally aspirated, and nature is the force. If there was no force, if there wasn't this super low pressure, almost a vacuum in the cylinder, that air couldn't be pushed in there, making hundreds or thousands of horsepower. Some naturally aspirated engines are well over 1,000 horsepower. It couldn't do it in that period of time. I mean, we're talking 100th of a second. We want to turn diesel engines well over 6,000 RPM. In fact, we have. So I've got the feeling you understand the four-stroke process now. So let's go back into Dyno 2 and talk about feeding the compressor. So what we've got inside here is a 4-inch diameter butterfly valve that we can finally adjust to duplicate the density at high altitude, the ambient air density, or duplicate the really lousy air density you get feeding the engine if this is underneath the hood. We're going to fire this thing, we're going to run the numbers and show you the horsepower lost. Before we get this thing running, there's a few things I'd like to explain. Engines pump cubic feet per minute. What are the units? Well, the units in my mind are pounds of air per 1,000 cubic feet of volume. How do you wrap your head around 1,000 cubic feet of air? Well, imagine a room 10 feet by 10 feet by 10 feet high. That's 1,000 cubic feet of air. What does that weigh? What's the mass of the air? Because you're mixing pounds of air with pounds of fuel in a certain ratio. It's called the air-fuel ratio. You want to hit the correct air-fuel ratio. You also want to make more power. If you want to make more power, it starts with pounds of air. What does 1,000 cubic feet of ambient air weigh? Well, the Society of Automotive Engineers have come up with a number of standards. The one that is used by all the automotive industry in the United States is called J1349. It describes the standard day's conditions and the air mass. On a J1349 standard day, the ambient air pressure is 14.4 pounds per square inch absolute. That's the pressure above a perfect vacuum. The air temperature is 77 degrees Fahrenheit, and the humidity is 0. On that standard day, 1,000 cubic feet of air weighs 72.2 pounds. We call this air density, 72.2 pounds per 1,000 cubic feet, a 100% day. This is the air mass that dyno correction factors correct to. This whole thing with correction factor, in my opinion, doesn't matter much unless you want to compare your engines with others in brochures when you're selling cars. What matters to you or I is the air density where we're at and the power we make there. Wherever we live or wherever our neighborhood is, wherever we street race, or wherever we race professionally, it's called observed horsepower. And the observed horsepower is what we give a damn about. What the corrected horsepower might be is immaterial. You don't have that. In fact, the conditions SAE corrects to have 0% humidity. That never happens. So I kind of like, okay, here in Azusa, California, our standard air density most of the year is pretty much that standard day air density, that's 72.2. It amazes me. Sometimes we've got really cold days. I call those horsepower days. Sometimes we've got a dry day and a cold day. That's even better. Why is that better? As the temperature goes up, the air density goes down. As the pressure goes up, the air density goes up. As the humidity goes up, the air density goes down. Wait a minute. If we're measuring boost pressure, we're not measuring any of that. We're not even measuring the total pressure feeding the engine, because boost pressure does not include the ambient air pressure. And that's part of what forces the air into the engine. I mentioned earlier that 72.2 pounds per 1,000 equals 100% day. But you don't have to have that 14.4 pounds and 77 degrees and 0% humidity. You can have a different combination. I've put together a couple examples here. Houston, Texas, kind of a typical day. The altitude there is 105 feet. Air pressure 14.7 pounds per square inch. Air temperature 76 degrees. Relative humidity about 72. That gives you 72.2 or 100% day as well. Here in Los Angeles, downtown, they're lower than us, 285 feet of elevation, 14.6 pounds of pressure, 73 degree day, 66% relative humidity. Once again, we got 100% day or 72.2 pounds per 1,000 cubic feet. Temperature is your enemy, pressure is your ally, and humidity is your enemy. You can't do a damn thing about the humidity. Mother Nature that's her trump card. But you can do something about pressure, and you certainly can do something about temperature. We're going to run a cold air intake with a slight density loss due to pressure and temperature gain. But it would be typical of a good cold air system. Then we're going to take that good filter and we're going to put it under the hood. It's hotter under there. That's not a good thing. You'll see why in a few minutes. And once you see why, then every time you look at a filter under the hood, you're going to think, this guy doesn't know, does he? It's all about horsepower. Why would you want to give a bunch away by putting the filter in a hot air environment? That's lower density air. In fact, our demo is going to increase the temperature 50 degrees. That drops the density to about what it would be at 4,000 feet of altitude on a typical day. You all know when you go to higher altitude, you lose power. Why do you lose power? You've lost air density. When you go into the dyno room, you might say, hey Gale, don't you call that thing a filter on a stick? Well, yeah, I do, but there's a difference here. It's not under the hood. The room has the same temperature as the rest of the shop and the outside air here. It's ambient air. We move 40,000 cubic feet a minute through that room, through these giant intake grills with monster filtration system on the ceiling up here and out to Mother Nature. So we're changing the air in that room many times a minute. And consequently, whatever the temperature is right here where we're sitting is going into that filter as well. First test will be that ambient air intake, a good system. The second test and the third test are actually the same test. There's quite a drop in density. We've took the higher temperature and balanced it with a lower pressure. I'll explain all that on the back side when we look at the data. Let's go ahead and take it up. 3,000 RPM, and nominally we're around 450 horsepower on this test sequence. All right, we're at 201 degrees out into the tower, 202 now. Let's go ahead and pull some power. We've got the butterfly completely open. There's no density reduction through the butterfly, just the filter and the intake tube. Here we come. Cylinder pressure is looking good, 160. Looking 450. Right there. There it is, 454, right in there. Yep. All right, let's go into the dyno cell and crank down that butterfly. We just closed the butterfly down, but one thing I want to say about that filter in there, that's what I call the first of my big ass filter program. That's the L5P, the Ford and others are coming. That filter is invisible to airflow. It's almost not there. When I saw the numbers off the flow bench, I went, go back and do it again. And sure as hell, it's just at 1,000 CFM, the thing's only dropping a few inches of water in terms of pressure drop. I've never seen an air filter quite like that in my entire life, and I'm pumped out of my gourd about it. We've restricted. We're going to drop the density to 50 degrees hotter or 4,000 feet of altitude, about 12.5%, 13% drop in air density feeding the compressor of the turbocharger. Let's pull it. Let's go ahead and pull it. See what we get for power difference. Data logging is on. All right, here we go, guys. Cylinder pressure's been pretty comfortable on these runs. It's kind of right around that 180 design. 183, I think it is actually. All right, pulling it up. All right, 3,000, there we go. Got the number. Okay, let's pull it back. And we will stop the data log. All right, there we go, data log stopped. And let's pull the SD card and go crunch the numbers. I've got a little condensed section here that I did. The actual amount of data, we're only going to look at a little bit, but this will give you some idea of the amount of data we've pulled off that SD card. A whole lot of this stuff is going to be really interesting as we proceed to try to kill this engine. Let's talk about the ambient conditions we duplicated and the hot underhood placement of the filter that we duplicated. Looking at ambient conditions, we've got a cold air intake, we've got an underhood hot air intake, both at the same altitude. Then we have a cold air intake at 4,000 feet of altitude. The difference at 4,000 feet is the pressure goes from 14.4 psi absolute to 12.7. Less pressure, less density. Ambient temperature at 64 degrees and the ambient humidity at 59% is kind of fixed by where we're at. The ambient air density, though, with that lower inlet pressure duplicated by that density valve, is different. Instead of being 73.5 pounds or 101.8%, almost 102% ambient air density, we're down to 64.4 pounds per thousand cubic feet or 89% ambient air density. So that's crippling when you go to altitude. But you don't have to go to altitude to get that. You can just put your filter under the hood and shut it and inhale that hot air. So what happens then? Well, we're 50 degrees hotter under the hood than we were outside. Instead of 64 degrees, we're about 114 degrees. That's that nominal gain of 50 degrees. That drops the density 13.4 pounds per thousand cubic foot or 18.6%. You basically end up with, instead of 95.7% air density at the compressor inlet, you're down to 83.4% in both these conditions. One, you can't help. You're at altitude. The compressor's going to have to work harder. The other one, you can help. Now, if you're at altitude and you have a hot air intake under the hood, that's really ignorant. That could happen, though. Running at high altitude can have that hot air intake as well. That's the worst possible combo. Let's have a look at the final results. We locked our boost pressure in at 28 pounds. We locked our air-fuel ratio in at 24:1. Our ambient density on both tests is the same. This is basically the 610 foot of altitude hot air under the hood test results. The 4,000 foot results would be the same. So let's run through what we got with a good filtration setup and a bad filtration, hot air filtration setup at the same altitude. The density loss through the filtration and the tube, etc., 6.1% with cold air and 18.3% with hot air. Pretty remarkable. So your compressor inlet density went from 95.7% down to 83.4%. Here's the thing, we're maintaining constant boost, but the next line item, which is the delta temperature or the temperature gain through the compressor on the turbo, went from 262 degrees to 333. What's up? Well, we're pushing the compressor, we're making it make the same boost, but it sure as hell isn't making the same density. Why? Because it's heating the air more to make the same boost. We're at 3,000 RPM. The engine is a 6.6 liter Duramax. It's pumping 350 CFM in both cases. But look at the mass airflow. We were at 58 pounds per minute with the cold air intake, and we're at 53 pounds per minute with the hot air intake, but the boost is the same. Wait a minute. What's going on? I'll tell you what's going on. The horsepower went from 454 to 422. We lost 32 horsepower. Same boost, same air-fuel ratio. Torque went from 794 to 738. We lost at 3,000 RPM, 56 pound-feet of torque. And here's the revealing thing. the compressor efficiency went from 76% to 66%. We lost 10% of the turbocharger compressor efficiency. That's why it's heating the air more. It's pretty obvious we're pushing the hell out of this turbo. And that will be the subject of episode number 5. Stay tuned. There's so much more to learn here, and I'm going to do my best to blow up this engine. If you're interested, all you need to do is subscribe.